Hello and welcome to this EE228 video on differential equations. In this video we're going to look at the second special case I can think of when needed when trying to solve diffEQs, and that is when the input or the forcing function contains a mode of your characteristic equation. That is, when the forcing function looks like one of your homogeneous terms. So let's look at an example again to illustrate why this is a problem and show you how to solve the problem. So for this example, let's look at, let's find the zero state response of the following system. Y double prime plus y equals cosine of t, and we'll do this for positive time. Okay. So if you were to solve this, if you were to try to solve this the naive way, you would say, okay, zero state response. That means assume zero initial conditions and just solve for the function y that obeys this inhomogeneous diffEQ and has zero initial conditions. So the first step in that would be to find the characteristic polynomial. So we've got one double derivative and one zero derivative, and we're going to set that equal to 0. So here the characteristic roots are, I call them R before, the roots are plus and minus the imaginary unit, or square root of -1, or just j. So that means that the homogeneous solution will look like C1 e to the positive jt plus C2 e to the minus jt, right? That's what we learned. Take the roots and give them each to an exponent and allow for linear combinations of those exponents. But if we're expecting a real function out, and we need to have a real function because we're being forced by a real function, then the sum of these two needs to be a real number for any given time. So that means that instead of a C1 and a C2, we must have a C and its complex conjugate, which I'm going to use the asterisk or the star notation to denote. Okay, so I'm going to go a little bit further in here just to show you why the cosine, because right now we've got two complex exponentials and they don't actually look like cosines. So you may be wondering, the input doesn't contain a mode of the characteristic equation, but I'm going to show you that that's not correct. To help simplify this equation, I want to write C in a special form. Because I know it's complex, or in general it could be complex, I'm going to let C be the magnitude of C times an exponential. And that exponential will be raised to j and the argument of C. So this is just a polar way of representing a complex number. And if we do this, then all of a sudden these two terms become magnitude C e to the jt e to the j angle C plus magnitude C. And what do we know about complex conjugates is that they have the same magnitude as their conjugate pair, but they have opposite phase angle. So C star, so maybe we can write that here. So if we write C this way, that means we can write C star in a very similar way as the same magnitude and the opposite angle. Okay, so e to the minus jt times e to the minus j angle C. So we can factor out the magnitude C and we can combine the exponentials, and we get e to the j times quantity t plus angle C plus e to the minus j quantity t plus angle C. And so here I hope you recognize that this is it's almost a cosine, right? This is e to the j blank plus e to the minus j same blank should get you cosine, except we're missing a factor of 2. So this, by Euler's formula, looks like 2 magnitude C times cosine of whatever was in that exponent. Okay, so before we had the homogeneous as the sum of two complex exponentials, but because those complex exponentials were complex conjugates, we can write it as a amplitude shifted and phase shifted cosine. The forcing function is also a cosine. So here we see that the forcing function is exciting one of the characteristic modes, and we say that because the frequencies of both of these are the same. This is a unit 1 radian per second cosine forcing, and this is a 1 radian per second natural mode of the system. So in this kind of situation, you're going to guess a particular that somehow looks like the forcing function. So for us, let's say that that is a times a cosine and b times a sine, right? This is the most general way to write a sinusoid. Incidentally, this could also be written as some constant d times phase shifted cosine. Right, these two are equivalent as long as we don't know anything about a and b. We have 2 degrees of freedom in this representation, and we have 2 degrees of freedom here, the d and the phi. Okay, I'm going to choose to work with this one because I think it makes the linear algebra work out a little bit nicer. So let's see if we can satisfy the forced solution. That would mean take the particular, yp, double prime it, add it to itself, and that has to equal cosine of t. So if you double differentiate this representation of yp, you'll get minus a cosine t minus b sine t plus a cosine t plus b sine t. Right, so here is yp, and here is yp double prime. But you'll notice that this term cancels that one, and this term cancels this one. So we're suddenly saying that 0 has to equal cosine of t. And this is, again, one of my favorite mathematical symbols, the lightning bolt of contradiction. So something went wrong. And that's this special case, is because the input, the cosine of t, appears in the homogeneous solution. So just like last time, the workaround in special case 1, when you had repeated roots in the homogeneous solution itself, you had to multiply your characteristic mode by a polynomial power of t, corresponding to the multiplicity of that root. We're going to actually take the same approach here. So it's a different problem, but it's actually a very, very similar solution. So the workaround is to increase in polynomial power our y particular. So that means that now the guess ypt will be a t cosine t and b t sine t. All right, so if we do that guess, it's going to take a little bit longer to differentiate it, so bear with me here. The first derivative, we're going to do a couple of product rules. Gets you a cosine t minus a t sine t plus b sine t plus bt cosine t. But we can't stop with the first derivative. It's a second order diffie, so we got to go up to the second derivative. So now we've got a couple of plain derivatives and the same 2 more product rules to do. So we get minus a sine t minus a sine t minus a t cosine t plus b cosine t plus another b cosine t, and then finally, I almost had it there, finally minus b t sine t. If you're wondering where all these terms come from, I'll try to draw it out. If you differentiate this, you get that. If you differentiate this, you get both of these terms. This differentiated gets you that, and lastly, the last term differentiated gets you these 2. Okay. And so now let's look at the forced solution with our updated guess. So the forced solution now is take yp double prime, add it to yp, and that's got to equal cosine. And if you do this, you'll end up with minus 2a times sine t minus at cosine t plus 2b cosine t minus bt sine t. Now that's yp double prime when you collect like terms. And we're going to add that to yp, which was at cosine t. I'm going to do it on the next line because I'm going to line up like terms. And bt sine t. So this is, again, yp double prime and that's yp. And so if we add up the right-hand side, that should be cosine of t. And what we get on the left-hand side is minus 2a sine t plus 2b cosine t. Now, you might be worried that we have a sine on the left and a cosine on the left and just a cosine on the right. But I want to assuage your fears by convincing you this is the same thing as saying 1 cosine t plus 0 sine t. And now we can again try and match like terms. So that means that minus 2a has to equal 0, and plus 2b has to equal 1. So by matching these squiggles with squiggles and dashed with dash, we can conclude that a has to be 0 and b has to be a half. Okay, I'm running a little bit out of room here, but let's try to utilize this bottom left corner. So our best guess at the zero state solution is going to be 1/2 times t times sine t, because that's our newly minted b that we found was b equals a half and a equals 0. So it turns out that forcing the system with a cosine, you don't need a cosine in your solution, but you do need a t times a sine t. So let's see if we can check our answer. And to do that, I want to redifferentiate this y0 state and make sure that it meets the inhomogeneous differential equation that we started with, and that also that it meets the initial conditions, and in fact the 0 initial conditions that we have by assumption when solving the 0 state response. So here we've got my best guess at y0 state. So let's differentiate it once, yzs prime, and we'll get 1/2 sine t plus 1/2 t cosine t. And if we differentiate that again, yzs double prime, we'll get 1/2 derivative of sine gets you cosine, and then product rule here, another half cosine, and then minus 1/2 t sine t. Okay, so the check is, does it meet the original inhomogeneous diffie q? Let's take y double prime, which is 1 cosine, and it's minus 1/2 t sine t, and we add it to y, which is positive 1/2 t sine t. So we do get agreement that this solution, yzs of t, meets the inhomogeneous requirements. And lastly, let's check the initial conditions. So y0 state at 0 is 1/2 times 0 times sine 0, which is definitely 0, check. And y0 state prime at 0 is what? 1/2 sine 0 plus 1/2 0 cos 0, which also equals 0. Awesome. So this solution is the 0 state response because it meets the inhomogeneous diffie q and it satisfies both 0 initial conditions. And you wouldn't have gotten that if you didn't know the workaround, that we had to increase our original particular guess to be just a mixture of cosine and sine. Now we had to increase the polynomial power of t up here. I wanted to take a moment and illustrate how you can use MATLAB to check the work that we just did. So again, we just solved the 0 state response for the differential equation that was y double prime plus y is being forced by unit frequency cosine. And the solution we got for that was y of t should be 1/2 t times sine of t. So again, everything in MATLAB is array based, so that includes the time variable. So I would like to create a time vector, or a vector full of time values, and I want to space them linearly, and we'll start at say -1 seconds, and we'll go to about 12 seconds. I know that the cosine is 1 radian per second, so it'll traverse 6 radians, nearly a full circle, in 6 seconds. So I'm going to look at nearly 2 cycles of the cosine. That's what dictates the end point for this t variable. And if you don't give a third argument to the linspace command, it defaults to putting 50 equally spaced points. That's going to be a little bit too coarse. I'd actually like to do something on the order of 10,000. Okay. So if I don't put a semicolon here, it'll print out all 10,000 of those points, but now the t variable is stored in the workspace, and I can use it to define the forcing function. So let's let x be cosine of t, but it's only for positive time or non-negative time. So what I want to do is I want to element-wise multiply the array that is filled with cosine of t values, and I want to multiply that by a logical array that returns true whenever t is non-negative. So again, this is an array the same size as the t, and it's filled with the cosine of those t values. This means instead of matrix multiply, I want to element-wise multiply, and I'm going to multiply by an array that's filled with booleans, zeros and ones, and ones where this statement is true, and zeros where it's false. So let's see if we can plot that here. So plot t comma x, and there we go. There's my cosine that starts at t equals 0 and is 0 beforehand, and otherwise it oscillates at 1 radians per second. Okay, I'm going to close that for now just to give us a little bit more screen space. And now I want to define the y, the ZSR that we solved for before. So that'll be y is 0.5 times t, and I want to element-wise multiply that by sine of t. And I want to element-wise multiply that by the same boolean, the same logical, because the y function is only valid for positive time as well. Okay, so how do I get, I've got my cosine, I've got my y, how am I going to get y double prime? So what I like to do is use the diff command. So I'm going to say dy is diff of y, and what diff does is it just takes y of 2 minus y of 1, and then it goes y of 3 minus y of 2, and then on and on and on and on. Okay, so it just takes the difference between adjacent members of the y array. Okay, but that's not the derivative, because the derivative is dy over dt. It's the difference in height of the function divided by the delta time. So we also need to define a dt, which is just the difference between any two points in my time vector. I just took the second and first. You could have just as easily taken the 100th and 101st. It shouldn't matter. So y prime, I'm going to call, is dy divided by dt. And I don't need to do element-wise division here, because dt is just a scalar, and an array divided or times a scalar is just every element in that array divided or times that same scalar. And then we're going to do the same procedure over again to get y double prime. So call it ddy is going to be diff of y prime. dt will be the same, so y double prime is going to be ddy divided by dt. Okay, so now I'm ready to plot the left-hand side. I need to add y double prime with y. And the only wrinkle in this plan is that the diff command takes an array of length n and outputs an array of length n minus 1. Do you see what's going on here? We're going to lose one length of the array because we're just taking pairwise differences. So the only wrinkle is I want to say plot t of 1 to n minus 2, because I know that y double prime is 2 shorter than y, and y is the same size as t. So I'm going to plot the first, all but the last 2 elements of t against y double prime plus y from 1 to n minus 2. Okay. And hey, look at that. We get the exact same thing that we just saw before. So to convince you that it's different, or to convince you that it's the same, actually, I'll plot t and x of t, and I'll plot it as red O's, and they line up exactly. Okay, so this is evidence that we have gotten the correct solution. Now, what we have plotted is not the solution; it's just the forcing function. If we want to see how y evolves with respect to time, I would make a new plot. So figure and new plot of t versus y. And here we see this is a sine wave that has an envelope that is increasing linearly with t, right? This is t times sine of t. Okay, thanks everyone for watching. I'll see you later.